Thanks, you too. Thanks. Have a good spring break. I'll see you tomorrow. I always do that.
So much. Spoon feeds you everything. Catherine is like you feed it with a stick repeatedly with those what you want, and then it still misbehaves.
Why doesn't your work use like answers? Oh yeah. The real question is, was it stitched or was it signed? Okay, it's 7 o'clock, so let's go ahead and get started. Good evening, everyone. It's our last class before our spring break. So how's everyone doing today? I know it's a mixture of EA, but also I know you guys have a project due or activity due on Friday, so don't be too stressed about that. I walked earlier too. I don't know why. I didn't walk you out. Someone else walked you out. More than me, that's for sure. Okay. And so today we're going to continue on with our lecture notes on finite element methods, or finite element. I mean, the whole class about finite element methods, but finite element forms. Okay. And so last time, we had a very math intensive class. And so today, we're going to start with an example. And so hopefully the example kind of shows you kind of everything that, how to apply everything that we learned last time. Because I know, what we did last time, I know can be really intimidating. And so hopefully, today we'll kind of, I won't say it won't, it'll make it less intimidating, but at least show you that you can actually conquer it. You can actually do these problems. Okay. All right. And so any questions on anything before we begin? I know you guys, I know a lot of you are working on the MATLAB code for the activity. And so remember, I do have office hours tomorrow from 1 to 2. And so if you're struggling with the MATLAB code, please please stop by if you can. But if you can't make it to office hours tomorrow, then you can send me an email as well. And so usually for MATLAB stuff, it's a lot easier if you send me your MATLAB code. And then I can kind of go through with the fine-tooth comb and kind of point out give you some feedback based on that. And so I'm always happy to do that. And so you can just send me your code and you can just be like, I don't know what the fuck's going on here, and I will do my best to kind of help you. Okay. So let's go ahead and pick up where we left off. So we left off last time talking about finite element forms. And so the whole idea with finite element forms is to take our weak form and turn it into a finite element problem. Okay. And by finite element problem, what I mean is basically an algebraic problem. Okay. And so if you remember from last time, we had a linear system that looked like this, right? And so we had K, where K here is our global stiffness matrix. Okay. This is multiplied by U, where U is our solution vector. Okay. And this is equal to F, which is our global forcing vector. Okay. And this was a linear system. And so we had, a matrix multiplied by a vector, which is equal to another vector, right? And so that matrix represents a linear system of equations. Okay. And so we've seen these before. And so, we've been building these, for the first 8 weeks of this class. And so, we had our global linear system, we had our solution vector, we had our forcing vector, right? It's just that the way that we obtained our element stiffness matrices was different before. And so we had kind of just based them, we kind of computed them just based on what the structural elements look like. And so we had element stiffness matrix for a truss, different one for a spring, different one for a beam, different one for a frame, right? Remember, what's different about what we're doing here is that we're not making any big assumptions of what our elements look like. We're doing these based on a governing differential equation. Okay. And remember, that's really the power of finite elements. And so finite elements, as a method, really where its power is to take a very complicated partial differential equation. In our cases, we're just doing ODEs, and then give us a way to solve for its solution, without actually having to solve the differential equation. Okay. And so, the approach here is fundamentally different because, we're not just doing it for very specific structural elements. We're doing these based on the equation. And so now this becomes much more of, the class, I think, now kind of takes a turn into much more of an applied math kind of flair to it, as opposed to an engineering flair. Right? And finite elements kind of as a method kind of exists within kind of the intersection of engineering and applied math. And so this is kind of the applied math side more so than the engineering side. Okay. And so, of course, we came up with expressions for our stiffness matrix and our forcing vectors but they're very long. And so, I think it'd be better to kind of show them in an example, before, instead of that. Okay. Okay, so that's kind of just a recap of last time and kind of the motivations of why we're doing that. And so are there any questions on this? Okay, so let's jump into an example. All right, so this example we have, I said that we have a rod that's attached to a wall. Okay. And so let's say that our rod here has a body force. And so let's say that we have B of X is equal to 2 newtons per meter. Okay. And so apparently we're on a planet with sideways gravity, I guess we can say. Okay. On this end of the bar, we have a fixed support. Okay, so our bar is fixed. And we're also going to have a pressure, a Neumann pressure on the right side. Okay, and it's going to have a value of -5 Pascal. Okay. Okay. And so we're going to take this domain. Oh, the length of the domain, that's important. The length of the domain is 20 meters. Okay, so we have a very long rod. And we're going to discretize this domain into just 2 elements. And so we're going to do a 2-element solution. Right, so the elements are not going to be the same size. And so we're going to have element A, element B. And so element A here is only going to be 5 meters long. And so the x coordinate for node 1 is going to be 0 because that's going to be at the origin. The x coordinate for node 2 is going to be 5. Meanwhile, the x coordinate for node 3 is going to be 20 on the far side. Okay. And of course, we have our solution variable u1, u2, and u3. All right, so based on this mesh, let's find the finite element solutions to for the nodal displacement values. Okay. Okay. And so we're going to have eventually we're going to have a global system that's 3 by 3. And so that's going to solve for U1, U2, and U. Okay. Oh. We also need the material properties. And so our Young's modulus, we're going to say is 5,000 pascals. Okay. Right, so we have a constant Young's modulus throughout the entire rod. But just to kind of show you the power of this method, we're going to have an area that changes as a function of x. Okay? So our area is going to be 1 plus x squared divided by 400. Okay. And so we have an area that varies with x. And so this is a problem. Normally you would look at something like this and say that's a truss bar. Like obviously I could solve this with truss equations, but because we have the body force and because we have the varying area, this is more appropriate to solve with the methods that we've been doing because we're equipped to solve for those kinds of situations. Okay. Okay. So any questions on the problem setup here? Okay, so let's go ahead and start solving this problem. Okay, and so we're looking for a finite element solution. Sorry, this thing changes to the eraser, totally randomly. Okay? And so we're looking for the finite element solution. Okay, and so we're going to follow the same process that we did for all our trusses and beams. Right. So the first step is our element stiffness matrices. Okay. But for these problems, we have to do an additional step. And so in addition to the element stiffness matrix, we're also going to have to compute an element forcing vector. Okay, and we're going to do this twice. And so we're going to do it for element 1 or element A and for element B. Okay. All right, so let's start with element A. And so for element A, the element stiffness matrix is equal to integral x1 to x2 of dn1 dx, right? Remember, these are the shape functions. dn2 dx, okay, multiplied by e times a. Then we have dn1 dx, dn2 dx, okay, dx. Okay. All right. Remember, n1 of x these are the shape function, remember? So this is x1 minus, or x minus x2 divided by x1 minus x2, okay? And n2 of x is equal to x1 minus x divided by x1 minus x2, okay? Right, so those are the shape functions for the two, two ends, for our system. And so we don't need the shape functions here, but we need their derivatives. And so let's go ahead and take the derivatives. Okay. So dn1 dx. Okay. We're just going to have a 1 divided by x1 minus x2. Okay. Then we have dn2 dx is equal to minus 1 over x1 minus x2. For this particular element, we know what x1 and x2 are. So for element A, x1 is equal to 0 and x2 is equal to 5. Okay. So let's go ahead and plug that in. And so if we have a 1 divided by 0 minus 5, we have a minus 1 over 5. Okay. And for n2 or dn2 dx, we have a minus 1 over x1 minus x2. And so we're going to have just the opposite of that. So we have a positive 1 over 5. Right, so this is nice. And so both of our shape function derivatives here are constants, which is good. Okay. This is one of the benefits of working with linear shape functions, because when you take their derivatives, you just get a constant. And so that kind of helps with the integrals quite a bit. Okay. And so let's go ahead and plug these in. Okay. We're also going to plug in for E and for A. Okay. And so if we plug these in, we have integral from 0 to 5, right? So that's x1 to x2 of the vector dn1. So we have a minus 1/5 and then a positive 1/5 on the bottom here. E here is 5,000. A is a 1 plus x squared divided by 400. Okay. And then we have a row vector of minus 1/5, 1/5 dx. Okay. And so let's go ahead and simplify this expression. So we have a let's perform the matrix, the vector multiplication here first. Okay. So we have a 1/5 minus 1/5 over 1/5, and then a minus 1/5 1/5. Okay. And so remember, the result of multiplying these two vectors is going to be a 2 by 2 matrix, right? And so that 2 by 2 matrix is going to be a minus 1/5, minus 1/5. Okay. Okay. Then up here we have a minus 1/5, 1/5. Okay. Then we have a minus 1/5, 1/5. Okay. Then we have a positive 1/5, 1/5. Okay. And so if we evaluate all of these multiplications here, we have a 1 over 25 minus 1 over 25 minus 1 over 25, 1 over 25. Okay. And so this is the result of multiplying our two shape function derivatives vectors by each other. Okay. And so if we put that together, we have an integral. We pop that into the integral. We have integral from 0 to 5 of this matrix right here. So we have 1 over 25 minus 1 over 25 minus 1 over 25 1 over 25. Okay. We still have our 5,000. We still have our a function, which is 1 plus x squared divided by 400. Okay. Now we have a dx. Okay. And so all I've done up to this point is I just took our two vectors there and I just did the vector-vector multiplication. Okay. And so because of their sizes, you end up with what's called an outer product. And so you end up with a matrix that results from multiplying those two vectors together. Okay. All right. Any questions about how we got here? Okay. All right. And so let's go ahead and simplify this. And so, we have a lot of constants here, so we can pull them out of the integrals, right? And so first thing I'm going to do is I'm going to take this 5,000 and pull it into this matrix here. Okay. And so we have 5,000 divided by 25, which is just 200. Okay. Then I'm going to take this matrix because it's all constants and then pull it outside the integral. And so if we do that, we end up with a positive 200 minus 200 minus 200, 200. Okay. And then we have integral from 0 to 5 of 1 plus x squared divided by 400 dx. Okay. All right, so let's go ahead now. Let's evaluate this integral. Okay. And so if we evaluate this integral, let me pull down this. We have a 200 minus 200 minus 200, 200. Okay. And so if we evaluate that integral, what we get is x plus x cubed divided by 1200. Okay. And we're going to evaluate this from 0 to 5. Okay. Right. And so if you plug in 5, if you plug in 0, you just end up with 0 everything. And so you plug in 5, what you get is the following matrix. Okay. And so you're going to end up with something, I don't have the intermediate value here, but it's equal to 5 point something. And so if you multiply that 5 point something by 200, you end up with a matrix of 1020.83 minus 1020.83 minus 1020.83 and then 1020.83. Right. And so this here is our element stiffness matrix for element 1. Okay. Right. So remember what I told you, before we started this section, that the process, the overall process of solving these problems is still the same. The biggest difference is how we're going to solve for the element stiffness matrices. Okay? And so you can see that on full display here. And so to solve this for this element stiffness matrix, we have to do some vector multiplication. We have to do a little bit of integration. But we end up with our element stiffness matrix, same as we always do. Okay. Just took a little bit of a different path to get here. Okay. Any questions on how we obtain this? Okay. All right, so that's the element stiffness matrix for element A. I'm sorry. And so now let's do the element forcing vector for element A. Okay. And so if you remember from last class, you know, this element forcing vector, this is a fairly new thing, and so we didn't deal with this before with trusses and beams, but you know, this is to express any kind of nodal forces that we're applying on our element. Okay, and there are two contributions to the element forcing vector, and so the first contribution comes from the body force term. Okay. One contribution comes from the body force. And so in this problem, we do have a body force, and so we're going to have a contribution from that. Okay. And the other contribution comes from any Neumann BCs that are being applied. So any kind of loads that are being applied, those get applied directly to our element forcing vector. Okay. And so this kind of changes a little bit of the order of what we've done before. So if you remember how we dealt with loads before, you know, we would always apply them at the end. And so here, you know, we're just kind of switching the order. And so, you know, we're just applying any loads, you know, to the elemental system, and then we're going to assemble it all at the same time. Okay. Okay. And so let's look at element 1. So let's go back up to the problem. Okay. Element 1 represents element A represents the element that's fixed to the wall. Okay. And so that represents basically this portion of the domain right here. Okay, approximately. Right. It's not to scale. You know, don't get a ruler out and measure how far off I am, but you know, you get the idea of what section this is. Okay. And so on this section here, you know, do we have any loads being applied on this element here? No, right? And so we don't have any contributions here. And so for this element, for element A, we're not going to have any contribution from the Neumann BCs because we don't have any loads here. Okay. And so we'll deal with the Neumann load on the next element, but for this one, we don't have to worry about that. Okay. And so the only contribution to the element forcing vector is going to be from the body force term. Okay. All right, so let's compute F1. Okay, so F1 is going to be integral from x1 to x2 of the shape functions n1, n2, okay, multiplied by the body forcing term, b of x dx. Okay. All right. So that's the generic expression for the element forcing vector contribution from the body force. And so let's go ahead and plug in for all these expressions here. Okay. So remember, n1 of x is up here. So n1 of x is x minus x2 divided by x1 minus x2, and n2 is x1 minus x divided by x1 minus x2. Okay. And so we have a constant factor of 1 over x1 minus x2. And so I'm going to go ahead and pull that out of the integral. Okay, because both n1 and n2 have it. And so this is a common factor. Okay. I don't know if my palms are sweaty or what, but I keep my iPad keeps kind of fritzing out. I need to eat more mom spaghetti. That's what I need. All right. N1. So N1 here, N1 is x minus x2. And N2 is x1 minus x. Okay. And our B our b function here is just a 2, and so it's just going to be a constant. So we have a 2 dx. Okay. And so here's kind of our first case of, we have different entries in the top and bottom. And so, we don't have just one integral that can apply to all. Okay. So let me go ahead and plug in for these values here. And so we're going to plug in for x1 minus x2. And we have 2, which we can pop out in front. All right, so we have a 2. And x1 minus x2 here is a 0 minus 5. And so it's going to have a minus 2/5 out in front. Okay. And then we have an integral from 0 to 5 of x minus 5, and then a minus x, because of we have a 0 for x1, and so we evaluate that, and then we just get a minus x right there. Okay. Okay. So now that we're at this point, we can integrate. Okay, so let's go ahead and integrate this guy. So we have minus 2/5. And so when you have different integrals here on the top and bottom, you have to integrate them separately. Okay, but you can basically just treat them as two separate functions that don't interact with each other. Okay? And so up top here, we have an x minus 5. And so the integral for that is x squared divided by 2 minus 5x. Okay. And on the bottom here, we have an integral of minus x. And so that's going to be a minus x squared divided by 2. Okay. And we're going to evaluate this from 0 to 5. Okay. All right. And so if you plug in these bounds, and so for the top here, we have a 5 squared divided by 2 minus 25, right? So we have 5 squared divided by 2, which is 25 over 2 minus 25. So that's going to be a minus 25 divided by 2. Okay. And then on the bottom there, we have a minus x squared over 2. So we apply our integration bounds, and so that's going to give us a minus 25 divided by 2. Okay. All right. And so now that we have these, we can just multiply our constants through. And so we have a minus 2/5 out in front. And so the 2 is going to cancel there. The minus signs are going to cancel out. The 5s are going to cancel out on top. Okay. And so we end up with a element forcing vector that's just 5 and 5. All right. So now that we have our element stiffness matrix, we have our element forcing vector, we can put them all together. Okay. And so our elemental system for element A is 1020.83 minus 1020.83 minus 1020.83 1020.83. Okay. U1, U2, right? Because those are the nodes that are attached to element A. And so let's not forget our fundamentals of keeping track of which nodes are connected to which elements. Okay. And it's equal to 5 and 5. All right, so there's our system for element A. Okay. All right, any questions? Any questions on this?
That's just for one element.
That's just for one element, correct?
So you have to do that again for the other element.
We were doing that again for the other element, yes. We'll go faster this time because I went slow on this one just to kind of explain every step. We'll go faster on the next one. Finite elements as a method was not designed to be done by hand, and that's kind of the challenge of teaching, is that to understand it, you kind of have to work through it by hand, but it's just not designed to do that. And so you end up doing these kind of very long, very time-consuming problems, but these are designed to be computer algorithms. That's kind of what they're designed to be. It was, but no one used it before computers. And so people developed a theory before computers, and then everyone said this is stupid because it takes too long. And so no one used it. But then once someone said that, we can turn this into a computer algorithm, that's when people started taking it seriously. Yeah. Mhm. Okay. All right. So let's so now let's do the same thing for element 2, for element B. Okay. And so just like element A, we're going to start with the element stiffness matrix. Okay. So KB is equal to integral. Now we're integrating from x2 to x3 because that's the balance for element B there. Okay. And so we have a dn1 dx, dn2 dx, okay, e times a, dn1 dx, dn2 dx, okay, dx. All right, so x2 is 5. It's a cursed 5. Okay, x2 is 5, x3 is 20. Okay. And so let's go ahead and plug that in. And so we have a 5 and 20. Okay. I'll give you a shorthand notation of dn1. And so dn1 dx. Okay. We know that from before it was equal to 1 divided by x1 minus x2, right? Another way that we can formulate it, that's a bit, in my opinion, a little bit more convenient, is said that dn1 dx is 1 minus 1 divided by the length of the element. And similarly, dn2 dx is equal to 1 divided by the length of the element. Okay, positive. And so the length of this element is just the difference between its two coordinates. And so we have 20 minus 5. And so dn1 dx is going to be a minus 1 over 15. Okay. And dn2 dx is going to be a positive 1 over 15. Okay. E is still the same. So E is going to be our positive 5,000. And then our A here is going to be a 1 plus x squared divided by 400. And then we have the same thing on the other side. So we have a negative 1 over 15 and a positive 1 over 15. Okay. All right. And so I'm going to take all our constant terms and bring them out. And so I'm going to go ahead and simplify and integrate this. So the integral is going to be the same as before, although the bounds are different. And so if we simplify and integrate, we get a 200 divided by 9 minus 200 divided by 9 minus 200 divided by 9, 200 divided by 9. Okay. And if we perform the integral, just like last time, we have an x plus x cubed divided by 1200. Okay. And this is evaluated from 5 to 20. And so if we plug in those integration bounds and we perform the arithmetic, right? That integration is just going to end up being a multiplying constant throughout, right? And so if we apply that, we get 479.17 minus 479.17 minus 479.17 and 479.17. Okay. So there's our element stiffness matrix for element B. And so this is like a little bit of a faster version, just so, just for the interest of time. Okay. So notice how, a lot of the effort that's associated with these problems. Well, the matrix multiplication might be a little bit of effort too, but a lot of the efforts also with regard to the integration. And And so that's, and you're not alone in thinking that. And so we're gonna learn a method later today to help simplify these integrals. Okay. Because I'll tell you right now, the people that wrote the codes, people that wrote ANSYS, they're not evaluating tons of integrals like this. And so what they're doing is they're using a method called Gauss quadrature to evaluate these integrals numerically. Okay? And it ends up being a little bit simpler than before. Well, I'll leave that up to you for you to decide, actually. So any questions on this? Yep. Oh, just scratching. Okay, so let's go ahead and do our element forcing vector. Okay. And so our element forcing vector is going to have two contributions here. And so it's going to have one from the body force. And another one from the Neumann BC. So let's do the body force one, because that's the same as before. And so we have a integral, okay, from x2 to x3 of n1, n2, b of x, dx. Okay. All right. And so if we factor out all the constants and everything, right, remember n1, n2 has an x1 over x2 from it. And so if we plug in for that, we say b here is equal to 2, then we end up with minus 2 over 15 integral from 5 to 20 of x minus 20 and 5 minus x, okay, dx. And so that was just a result of plugging in the numbers and just simplifying. Okay. From here we can integrate. And so if we integrate this guy, we have a minus 2 over 15. Okay. We integrate x, we get x squared divided by 2 minus 20x. Then we have 5x minus x squared divided by 2. We evaluate this from 5 to 20. Okay. And so if you plug in the numbers for all those things, you plug in 20, you plug in 5, you perform all the arithmetic. What you get is 15, 15. Okay. Right. So notice that we get kind of a constant. You can see that we have the same body forcing values for both nodes, right? And so you have 15 and 15. That makes sense because our body force in this term, b of x, this is just simply constant all throughout. Right. We might have problems later on where our body forcing is variable. Okay. And so for the cases where the body force is variable, that will give you, a variable f vector. But since the body force here is constant, it makes sense that our f vector here is also constant as well. Okay. Any questions on this? Okay. All right. So that's the body force contribution. Now let's do the Neumann BC. Our formula for the Neumann BC was the following. So we have n1, n2 multiplied by the area times the force. Okay. But all of these are going to be evaluated at the Neumann boundary. Okay. And so that means we evaluate everything in this parentheses at the Neumann boundary. And so it would help us, if we knew where the Neumann boundary was or what the coordinate was. And so for this problem, the Neumann boundary is at the very end of the domain, right? And so it's at the far right side. So if you scroll back up here, scroll, right? The Neumann boundary is on the very right side. And so what we can say is that the Neumann boundary, this occurs when x is equal to 20, right? So in other words, we're going to plug in x is equal to x3 into our Neumann boundary. Scroll back down here. Okay. And so what I'm going to do is I'm going to take all of our expressions here for the shape functions, for the area function, for the traction is just a constant, and I'm going to plug in x is equal to x3. Okay. All right, so let's start with the shape functions. And so the shape functions, we have a -1/15 out in front. Okay. Then we have an x minus x3. Okay. Then we have an x2 minus x3. x2 minus x, I'm sorry. Okay. And then for the area, we have 1 plus x squared divided by 400. Okay. And then our t-bar here is just -5. Okay. Okay. All right, and so now let's take this expression, and everywhere that we see an x, let's plug in 20 basically, okay? And so we have a -1/15 times 20 minus x3, which is 20, okay? Then we have a 5 for x2, and then for x, we're going to plug in a 20 for that. And then for the area, we have an x there, and so we're going to plug in 20 for x, divided by 400, multiplied by -5. Okay. All right. And so if we evaluate these, we have 20 minus 20, which is 0. We have a 5 minus 20 here, which is a -15. Okay. -15. And so that -15 is going to cancel out with the -1/15 on the outside. And so we end up with a 0 and 1. Okay. Next, we evaluate the area. And so the area, we have a 1 plus 20 squared. 20 squared is 400. And so we have a 1 plus 400/400. And so we end up with a 2. Okay. And then finally, we have a -5. And so the -5 here is just -5. There's no change for that. Okay. And so our contribution from the Neumann boundary condition is going to be a 0 and then a -10. Okay. And so there's our contribution from the Neumann method. All right. So I know we're taking a long time with these problems, but there's a lot of detail in these solutions. So I want to make sure I cover kind of every detail, so that when I kind of let you guys loose and try this on your own, then you have kind of you have an example that goes over each of these details, so you can kind of refer back to it. Okay. Any questions on this? Okay. All right, and so that's the Neumann load, and so let's go ahead and put it all together. And so the elemental system for element B and so for the element stiffness matrix, we have a 479.17 minus 479.17 minus 479.17, 479.17. Okay. Then we multiply this by U2, U3, okay? Because element B is connected to nodes 2 and 3. And on the right here, we're going to take our two contributions to the forcing. And so we're going to take our contribution from the body force. So our body force was 15 and 15, okay? And then we're going to add our contribution from the Neumann load. So we're going to have a 0 minus 10. Okay. And so, of course, if you apply this, becomes 15 and 5. Okay. And so that's our elemental system from element B. Okay. All right, but that's all the new stuff, and so that's the hard part. And so now we can do a part that we're all familiar with, which is assembly. Okay. So now that we have the element stiffness matrices for A and B, as well as our elemental forcing vectors, let's just assemble the giant system. All right, and so our assembled system here is going to be a 3 by 3. Okay. So let's have U1, U2, U3, okay. U1, U2, U3, okay. And on the right here, I'm going to leave it blank for now, okay. All right, so let's do element 1 first, or element A. Okay. And so element A is U1 and U2. Okay. So that's going to be these guys right here. Okay. But in addition to that, we have to put in their forcing vectors. And so their forcing vector is going to go into the right-hand side, just like that. Okay. Then element B is going to be nodes 2 and 3. And so that's going to be these guys right here. Okay. And we have an overlap on these two, just like that. Okay. All right, so this is familiar. And so, I'm going to go ahead and evaluate these. And so we have a 120.83 minus 1020.83 minus 1020.83. Okay. The positive 120.83. And then on the right, we have a 5 and a 5. Okay. And then for the for element B, we have a plus 479.17 minus 479.17 minus 479.17. And a 479.17. Okay. Then we have a plus 15 and a 5 right here. Okay. All right, so let me go ahead and clean this up because we have to add in our zeros as well, because this is 0, this is 0. Okay. And so if we clean this up, we get 1020.83 minus 1020.83, 0 minus 1020.83. Here we have a 1500 because the two added together. Minus 479.17. Okay. 0 minus 479.17, 479.17. Okay. U1, U2, U3. Okay. And on the right-hand side, we have a 5, we have a 20, and a 5. Okay. Right, but wait, we're not done yet. And so, we've forgotten one very important part of the process. Okay. We have to apply our fixed constraint. Okay. And so our fixed constraint, remember, we are fixing node 1. And so that means we're going to take our first row here and do what we usually do. And so we're going to zero it out. Okay. And that includes the right-hand side here. And so we have a 1, 0. Okay. And then just to make sure that our first displacement is 0, then we put a 0 in the forcing vector as well. Okay. Right. And so with that, now we're done. And so now we can finally solve this system. And what we get is U1 is equal to 0.0, U2 is equal to 0.0245, and U3 is equal to 0.0349. Okay. Okay. So all that worked for 3 measly decimal places, one of which was 0, which we already knew beforehand. So we did all that work for two decimals. All right, any questions on this? Any complaints about this? I know it's a lot. I know it's it's a lot. It's a lot of very tedious calculations, and unfortunately, that's kind of what finite elements is, because a lot of these, like I said, is designed for computers. And so, when humans try to do it, we can do it. We're not, we're not as fast as a computer, but we can still do it. But it just kind of takes up a lot of time. So, I know it's okay to complain. You can complain to me about how this sucks. I know. I had the same complaints about this stuff when I first learned it too. But I think what's cool about this class is that you can kind of see both sides. And so you can see, how annoying these problems are to do by hand, but you can just feel how powerful you feel when you tell a computer to do it, and a computer just kind of does this all kind of more or less automatically. So, that's kind of what this class is. So we kind of swing between, I want to kill Professor Tran to, wow, this MATLAB script is really cool. I think that's beautiful. That's a beautiful thing. Assuming I make it out alive by the end of the semester, then it's beautiful. Okay. All right. So let's go ahead and yeah, we all need some mom spaghetti after this. Okay. And so, we're not going to do another example. And so, I think that was enough. And I think everyone kind of got the point from all this. And so let's talk about something different. Okay. And so let's talk about integration, because that was kind of a big part of what we just did. But programming a computer to do integration is actually not the most simple and straightforward thing to do. And so we need a technique for this. And so that technique is called Gauss quadrature. All right. And so, a lot of the previous process, believe it or not, a lot of it can be automated. And you've actually already seen those processes automated already. And so you've seen the process of, of doing computations for element stiffness matrices. You've seen the process of, of assembly. You've seen the process of applying a fixed boundary condition. Okay. One thing that's hard to program, or that we haven't seen how to program yet, is how to integrate. Okay. And that was kind of I would say kind of the hand bottleneck in the previous example, where, you can tell a computer to do a lot of those things, but it's hard to tell a computer to take this integral here and evaluate that. Okay. Because integration is kind of an interesting thing. And so, you know, if you're integrating something simple like a polynomial, which is kind of what we did, you know, that's more or less straightforward. But if you think about all the really weird integration rules that are out there, like if you're integrating, you know, sine or cosine functions, or you're integrating an exponential times a cosine function, or you're integrating, you know, all these different kinds of things, there's lots of weird rules that you have to memorize. And that's really hard to kind of encode into a computer. And so finite element methods kind of run into this bottleneck where, you know, we have these integrals that we have to compute, but, you know, it's hard to kind of, you know, if we have to evaluate these integrals by hand and then plug it into a computer, that kind of defeats the purpose of having a computer to do all this work for us. Okay. But fortunately, you know, there's a better way. And so, you know, what we're interested in these integrals is not really the antiderivative itself, but what we're interested in is, you know, the final product. So after we plug in the integration bounds, and, you know, we end up getting more or less a number from this. Okay. And so let me kind of illustrate that with the last example. And so one integral that we had to perform in the last example, it wasn't the hardest integral in the world. Okay. So we had an integral from 0 to 5 of 1 plus x squared over 400. Okay. And so if we perform this integral, we have x plus x cubed divided by 1200, right? We evaluate this from 0 to 5. Okay. This part right here, right? That part right there where we you know, we basically took our integrand and we performed the antiderivative to get that. We don't really care. We don't really care what that is, right? We only care about what comes after when we apply the integration bounds. Okay? And so what we call that is, we call that kind of evaluating the integral. Okay, so we only care about the evaluation of the integral, not the integrating itself, not the antiderivative. Okay? And so luckily, you know, there's a method for getting the result of an integral without having to take the antiderivative. Okay? Okay. And those methods are called numerical integration, Gauss quadrature, just like the title of this section. And so the idea with Gauss quadrature is that if you have the integral, and let's say that this is evaluated at, I don't like these symbols, but I might as well use them because they're standard. Okay. Okay, so these are zetas, okay, or at least my attempt at drawing zetas. And so if you have to take an integral of some function f, okay, instead of taking the antiderivative of f, what we can do instead is we can take the integrand. Okay, so this is the integrand. The integrand is basically just the function that you're integrating, and you just evaluate them at key locations, you know, between the integration bounds. Okay. So let's call this epsilon a or zeta a plus f of zeta b. Okay, and so on and so forth. Okay, and so you're just taking a sum of evaluating the integrands, you know, at different locations. Okay, the trick here is that when you take these, when you evaluate the integrand, you add some weights to it. Okay. Okay, where the weights are just simple numbers, and so the weights are just going to be either 1 or 2 or something like that. Okay? And so what we're doing instead of performing the integral, what we take instead is a weighted sum of the integrand. Right. And so if you choose these sum locations, if you choose the weights correctly, right, if you choose them very carefully, then you're going to get the evaluation of the integral without having to perform the integration itself. Okay. Right, I'll give you kind of one very simple example. So this is the 1 point Gauss rule. Okay. And so if you have an integral between -1 and 1 of some f of zeta, d zeta, okay? What we say is that one way that we can evaluate this integral is if we take f, we don't take its antiderivative, we just take f just as it is. We plug in zeta is equal to 0, right? And then we multiply it by 2. Okay. That's it. And so we just take whatever integrand's there, we multiply by 2, and then we just evaluate it at 0. And that's your integral right there. Okay. So that's the 1 point rule. Okay. Right. There's a 2 point rule. And so the 2 point Gauss rule is if you have an integral from -1 to 1 of f of zeta d zeta. Okay. Another way to integrate this is we can take the integrand, we evaluate it at -1 over √3 plus the integrand evaluated at +1 over √3. Okay. So that's the 2 point Gauss rule. So we make 2 function evaluations there. Okay. And the last one I'll show you is the 3 point Gauss rule. And this one is if we take 5/9 times our integrand at a -√3 over 5 plus 8 over 9 times our integrand evaluated at 0 plus 5 over 9 times our integrand evaluated at +√3 over 5. Okay. So that's our 3 point Gauss rule. There's a lot more, and so there's you know, I think people evaluate this up to like dozens of Gauss points, which are not practical at all, but you know, mathematicians, they have to do something, I guess, and so that's how they spend their time. Okay. And so generally speaking, you know, if as you add more points, right, or in other words, as you do more work, you end up with a more accurate integration estimation. Okay. And so the thing with Gauss quadrature is that you it's only an approximation of the integral, and so you're not guaranteed to get exactly the same thing as if you would evaluate it, as if you evaluated the integral analytically, but you do get pretty close. And the more points that you add, and so as you go from 1 point to 2 point to 3 point, you get more and more accurate. Okay, but these locations and these weights have been optimized to make sure that you maximize the accuracy as much as you can. All right, so the next thing we're going to do, just to prove to you that it works. And so, I know the first time I always present this, everyone's like, there's no way that this works. And so, just to kind of prove to you that it works, we're going to do an example where I do it both ways. And so I'm going to do it analytically, and I'm going to do it with Gauss quadrature, and you'll see that we get the same thing. But before we do that, are there any questions on this? Okay, so let's go ahead and do that example. All right, so let's do the integral. from -1 to 1 of the function 3x squared minus 2 dx. Okay. And let's evaluate this integral. Let's evaluate it analytically. And let's evaluate with the 2-point Gauss rule. Okay. All right, so let's evaluate this analytically first. And so we take the antiderivative here. We have an x cubed minus a 2x, okay? And we evaluate this from -1 to 1. And we plug in the integration bounds for this, and we get a minus 2. Okay. Right. So this is analytically. So this is how we've been evaluating integrals before. Okay. So now let's do the same thing with the 2-point Gauss rule. I know for a problem like this, you know, I know it's really silly. You know, we literally did the analytical one in just, you know, 2 lines in 10 seconds or 1 line in 10 seconds. You know, but I want to show you that this works. And once we start doing problems with more complicated integrals, especially when we start going to 2D, then Gauss quadrature will be a godsend in those cases. Okay. And so let's take our integrand here. And so our integrand is 3x squared minus 2. Okay. So let's evaluate that at the 2 Gauss points. And so let's evaluate one at -1 over root 3. Okay. And we'll evaluate it at x is equal to 1 over root 3. Okay. And so we evaluate this at -1 over root 3. We have a 3. 3 had like a Pinocchio nose. Okay. So you get 3 -1 over root 3 squared minus 2. Okay. And we evaluate the integrand at 1 over root 3. So we have 3 times 1 over root 3 squared minus 2. Okay. And we're going to add these together. And so we have a 3 times 1 over root -1 over root 3 squared is just 1 over 3. And so we have a 1 minus 2. Okay. And this is going to be a plus. 1 over root 3 squared is 1 over 3. And so we have a 1 minus 2. Okay. We have a 1 minus 2 plus 1 minus 2 is equal to -2. Right. And so in this case, you know, for a very simple 1D integral, you know, the Gauss quadrature just does end up being a bit more work. You know, and so, you know, I feel like I've been apologizing a lot today because, you know, I said, you know, this method, you know, I'm hyping it up to be really cool, but, you know, it's actually a lot better in a computer. And so Gauss quadrature is another one of those things where, you know, it's really meant to kind of help a computer more so than hand calculations. All right. Any questions on this? Okay. And so probably, you know, one thing that you're wondering is that, you know, all the integrals that we've been doing are only between -1 and 1, right? And it would be a good observation. And so, you know, one thing that I haven't said yet is that Gauss quadrature, you know, these locations and these weights are only valid when the integration bounds are -1 to 1. Okay? Okay. And so that seems like a big weakness, right? Because, you know, we saw in the last example that we had a lot of integrals where, you know, we evaluated the integration from, you know, lots of different bounds. And so, you know, -1 to 1 is very restrictive. Okay? The good news is that you could take any integral and you can actually transform it to have any bounds that you want. Okay? And so that technique is called the change of coordinates. Okay. And so through a change of coordinates, we can take any integration bound and transform them into -1 to 1. And so in other words, we can take any integration. So let's say that we have a generic integral here from x1 to x2 of f of x dx. Okay. We can transform this into an integral from -1 to 1. Okay. Granted that we perform a change of coordinates, and so instead of x right here, we are now integrating with respect to zeta. Okay. As we have x as a function of zeta. We have this new term here called dx d zeta. Okay. And of course, we're integrating over d zeta right here. Okay. And so here we have our original integral. And here we have the change of coordinates. And then if we perform this transformation, then we can apply Gauss quadrature, okay? And so the process usually goes, if you want to use Gauss quadrature for your integrals, is that you take your integral, you first transform it into what's called a standard form. And so you transform it into an integral from -1 to 1. And you take that standard form integral and you apply Gauss quadrature to that, okay? And so, I unfortunately, I have to leave you hanging just because we are just about out of time. But I did want to give you a name for this guy, because this guy is going to be very, very important for us, especially as we move into 2D finite elements, which is what we're going to do after the break. Okay. This guy's name is the Jacobian. Okay. Yeah, so the guy that came up with this, his name was Jacob, and so he named it after himself. So we called it Jacobian. Right? And so what it is basically is that you can think of it as kind of like as a conversion factor between our original integration bounds and our change of coordinates here. Okay. And so when we come back from break, we'll kind of pick up right here. I'll do a bit of recap just because I know the week is kind of a long time. And then we'll pick it up from here just to see what the Jacobian is and what role it plays in this change of coordinates. Okay. All right. Any final questions before we wrap it up for break? Yep.
Do you know when you're going to do like 1 point, 2 point?
Yeah, that's a good question. So the question is, when are we going to use 1 point to 2 point Gauss quadrature? It really depends on your degree of laziness usually. And so most of the time for a lot of finite elements, a 1 point Gauss quadrature is actually just fine because you use linear functions. And so the thing is with linear functions, if you use a 1 point, you end up with an exact expression. And so it's usually not practical to go beyond a 1 point Gauss. Yeah. Mm-hmm. Yep. Oh, and I know this. I saved the bad news for the end, and so I know our activity is due tomorrow. But we've covered kind of a lot of content ever since we did the MATLAB stuff, and so we did strong forms, weak forms, and this week we're doing finite element forms. And so I am going to post another homework assignment. After activity 2 is due. But that's not going to be due until a week after spring break. But I wanted to give you at least a 2 weeks head start on that one. And so I know that there's work assigned over spring break, but it's not going to be due until a week after that. But I do want to give you a heads up before I do that. Okay. All right. So thank you everyone for tuning in. Oh, question? Yeah. So the activity is due on Friday, and then I'm gonna assign another homework after that. But it's not going to be due until a week after we come back from spring break. Oh, no, yeah. So the activity due tomorrow, but the homework's not gonna be due. I'm gonna assign it on Friday. I mean, the activity due is due Friday. I'm gonna assign the new homework on Friday, and then that's gonna be due a week after we come back from break. Yeah. All right, so thank you everyone for coming today. I know it's always hard right before the break, especially doing all this intense math stuff, and so I appreciate it. And so I hope you guys enjoy your break. You know, if you have any troubles with the MATLAB stuff, you know, please reach out to me. You know, I'm always available to help you out. And then I'll see you after that. Okay? If you're here to pick up your exams, I have them here, so you can come up to the front and pick up your exams. Yeah.
Sorry.
All right, and so I'll see the rest of you after the break. Thanks, everybody. Yeah, Tristan, to answer your question, Remont sums, they are more expensive because they require more evaluations. They don't scale as well as for being accurate for low you know, for low numbers of terms. Yeah. Mhm. Yeah. Okay.
I think we're both right.
Yes.
I don't think I end up because you're not calling.
Sure, we can check. So if you what was your equal? First row.
That's what I'm saying. My first row shouldn't be all zeros, but I mean, I can find mine.
I mean, look at yourself. I have a friend as a physical therapist.
Fair enough. I got a 1% trade off. So I just control them.
Yeah.
I was a little unsure about how I should set everything.
Yeah, usually the assembly is where I think that's okay, that's good. That's two. Perfect.
Yeah, this is where I'll. It's like the same as set.
I see. So this is the top left portion.
Right.
So these should all be ID because this is associated with the so ID line. Same thing on this. Exactly. Yeah. Because this is the top left. So this is like U1X, U1Y.
Yeah.
For a column, U1X, U1X. So like ID1 is associated with that.
Yeah, I was assuming what's off is going to be bucketed with the 2x. Right, it's not like 2x2 of only the x. I'm sorry, only the first number.
March 28th.
I mean, this is top left. So this is 91 for the row, but 92 row. So this is
Yeah.
91.
Oh, wow.
So I just finished the.
This is row 1. So this should be 2. So this should be 2. All these rows.
You should say.
I think you had
Oh, you changed it, IND.
yeah. Yeah, so for the top left, yeah, so the top left is all the nine.
I actually signed it.
Okay.
So think of it like this, so like for,
And I
and
showed
so for matrix, like this, that's like one,
Yes.
so it's the same for trusses.
I was just making sure.
Right up here. So this section up here is like both one. So
Yeah.
that's why we have 91, 91 row.
I didn't have a quiz like
The
that.
top right,
Oh, no, that's from out of class.
the top right, we have those one for the row. So we get 92.
Good.
92 as well. So down here, bottom left, we have no two for the rows. So that's going to equate to 92. And for the column, you have 91. We did everything else. It's just, yeah, it's just the top left. Those one.
Yeah, I'm looking at.
Yeah. I looked at the first one's good.
Okay, cool.
Yeah, looks good. Great.
I appreciate it.
Yeah.
And the rest of it should be,
Awesome. I'm lazy.
It's all good. I want to stay up to date. I don't use answers at work. I mean, because I'm in science, so I don't have a lot of final element stuff. It's just like, I kind of like told them, hey, like,
Nice.
but yeah, it's nice to stay, like. All right, Jake's probably not gonna figure this out. Thank you.
Yeah.
Professor, you're like, I write detailed notes.
Yeah.
This tells me nothing.
Oh, yeah, because the temperatures was also something I wanted to just sort of into the solution.
Oh, okay.
And so a lot of people, and so I should have moved this down here, so that's why I always took off point off, because people just looked at these underlying terms. But the temperature was also something else. So everything else that you sorted, so thermal conductivity.
Jake, I probably know that it's 68 degrees. Right?
The temperature.
I thought you were just emphasizing.
Yeah, I should have put it down here. That's why I took off. But it was like, it's tough because like about 60% of people got the temperature and they put it down there. And 40%, so I gotta reward the 60% that saw it. So that's why.
That's fine. I was- thank you.
Yep. Yes. Sorry. So this is the frame. Let's look at your codes. Yep, 5 kilograms. 1, 3, 2. I think all of those are. Let me just double check. Their proximity area. So the length, so only the last element is 25. That's this one. So the rest of them are 0.2. So all these. Technically, this one I put 330 for this one because this 4 here, the 5 here, so you rotate around. But if someone pointed this out, and I never noticed this before, but if you're 180 degrees out, then you end up with this because we have all signed close. So this should be okay.
Goes to the lower. So lower, that's why. Oh, shit, I gotta fix that. I just
Oh.
threw it on there, I never fixed it.
Oh, yeah, so that should be for node 5, right? So that should be 13, 14, 15.
I never changed. Oh, this is 13.
Oh, wait, so these are pin nodes. So for pins, the rotational aspect is not. And so it's only if you want to, because 1 is U1x, 2 is U1y, but 3 is theta. And so theta 1 is 3 and theta 5. And so that means your derivative is going to be 1, 2.
I didn't write it up either, so this one's. So this is gonna be 1, 2, 3, 4, 5, 6, 7, 8. This is gonna be 10, 11.
It should be. Let's try this. I know it doesn't make a difference in the trust.
I would go. And just compare that, all the things that you have to do. Everything else looks right. You can do kind of a side. Already here, it's my question. Yeah, the thing is with these, like one small. So you might actually really close to sheet. Last one is just.
in the last one. All right, let's start.
It's like, oh, I was lazy, bro. We literally had this conversation yesterday. I think it's halfway through.
Below the first page, the column did not say that all that.
I said I'm gonna let you figure it out.
And I did. Dr. Van-
Yeah, it's like
Dr.
serious.
Van says it looks good, but he just made a small mistake section. I mean, I figured it out way quicker than him.
Probably not.
Probably took more of that.
I don't know how long it takes.
I have to take a closer look. It is getting a bit late too. So, if you, for now, just so that you kind of move on, I would take your top, so your top portion looks right. So I would download this right at the end code and just copy and paste everything from here and replace that top portion of the code. And so just replace that and that should give you the right answer. The difference is somewhere, I think it must be something. Yeah, it's a very small one. Very. Yeah, and so there's something really small. So kind of the best thing for this is just to kind of start fresh a little bit and see what goes on there. So I do want you to start on trust. So
So I can just download this.
yeah, it's a .NET file, so you can just download that, right? Yeah.
You're right, you're code.
Alright, so let me talk. And then, if you're still struggling with it, just send me an email. You can help. Sorry about that.
No worries, I'll just get it, not this correct.
Okay. Is this for the frame or is this for the truss? Right, okay.
I'm just gonna trust.
I did the same frame problem for truss and just remove the rotation.
Okay. This is the same color I was looking for. Okay, so here's something. So the way I program this is that it assumes that the lower number node goes first. So it should be 2. Oh, it didn't work so. That's right. And it should be. I usually just keep the first one. The first one's good. So the first one, look at -0.003. That's good. And then do 2x. The thing is, like, these are too small, and so they don't show up here, and so the best thing is you do. Okay, yeah, so the first two match, then it's very likely it's gonna, so we have a minus 0.003, and then a minus 1.13. E minus 1. Yeah, yeah, so when you're doing the connectivity, make sure you do the lower number first, and then, yeah. Yep. Oops, I have to zoom on.